Well, I should tell you in advance that I have two confessions to make. First of all, I'm very intimidated being in front of you. I'm used to giving lectures to scientists and physicians. I've done some with maybe 4,000 or 5,000 people in the audience. I teach the Harvard medical students, but I've never dealt with patients per se, and this is a real challenge. The second part of my confession is that I'm not part of this lupus club. I'm a hematologist, and I specialize in blood coagulation. And as many of you probably know, patients with lupus, as well as patients with antiphospholipid syndrome, have problems with clotting. They have too much clotting. And so I'm here to tell you a little bit about how I've been drawn into this club as part of an effort to see if we can't understand as well as develop new therapeutics for thrombotic disease. Now, you've already heard my brother here. He's my younger brother, by the way, I should tell you that. And he's a card-carrying member of this club. I was here about 10 years ago. He invited me to his hospital to give grand rounds, medical grand rounds, to the staff and faculty, as well as then to give a research seminar. And during that research seminar, he heard, probably for the first time, a little bit about what we were actually doing in our laboratory. And he had the bright idea that this technology that we had developed should be applied to solve some of the problems in lupus. So he urged me to get involved in research with lupus, and I would say it probably took about 3 or 4 years before we really got started, but we did get started, and that's what I want to tell you a little bit about today. Can we turn the lights down a little bit? And let's see how this thing works. I just turn this off. Well, let me tell you a little. I have to give you the medical student lecture to educate you a little bit about clot formation, about thrombosis. First of all, this is, at least from 2007, the leading cause of death in the United States. Number one is heart disease. A lot of people don't realize that heart disease is number one. They think cancer is number one, but heart disease is number one and cancer is only number two. And stroke is number three, and so on and so forth. But if we look at which ones are associated with thrombosis, heart disease is about thrombosis. It's about heart attacks, myocardial infarction, which is caused by clots in the heart. Stroke is also about thrombosis, and cancer, the leading cause of death in cancer is the cancer itself, but number two in cancer is thrombosis. So thrombosis is a very serious problem. And approximately a third of patients with systemic lupus develop thrombotic complications. Those complications, just to use the medical terms, include venous thromboembolism, pulmonary embolism, you may know that as PE, deep venous thrombosis, DVT, arterial thrombi associated with stroke, and of course heart attacks, myocardial infarction. Both veins and arteries are susceptible to thrombosis in lupus and in the antiphospholipid syndrome. There are a number of tests that are used for predicting thrombosis in patients, and this includes the lupus anticoagulant. I bet you've all heard of the lupus anticoagulant. The lupus anticoagulant is a total misnomer. It was defined in 1972 by a very good friend of mine, and it was identified in 2 patients with lupus, but it can be associated outside of lupus, and it's not an anticoagulant at all. It actually causes coagulation. It causes thrombosis. But nonetheless, we still call this protein in the blood the lupus anticoagulant. Anticardiolipin antibody is another biomarker that is used, and anti-beta-2 glycoprotein 1 antibodies is another test that is used routinely to predict who's at risk to thrombosis. I need to teach you a little bit about thrombus formation. So I've taken this slide, I've been using this slide I think for about 35 years to teach medical students. It's actually stolen from the Scientific American. And do I have a pointer here? Oh, the yellow one, okay. Good, good. Okay. Blood coagulation is about maintaining a high pressure circulatory system. We all have elevated blood pressures. And that way the pump, the heart, circulates the blood around the body. And when we get a hole in our blood vessels, we need to stop it from bleeding or else we're going to exsanguinate. So we have a system in which platelets fill up the hole through a mechanism that's called platelet adhesion, and then those platelets bind to each other, forming platelet aggregates, and that forms a platelet plug, which plugs up the hole, and then ultimately a blood clot forms with fibrin to actually close the, stabilize the platelet plug. The whole idea is to maintain a high pressure circulatory system. So it's a host defense mechanism. And if we look at how blood clots, I'm not going to go into detail. I'm certainly not going to test you on this. But we can see that there are a whole bunch of proteins in the blood that participate in a cascade that transfer a signal from a protein called tissue factor all the way down to the generation of the fibrin clot. That's what you actually see when you cut yourself. So we have a mechanism of actually activating one protein after the next, after the next, after the next. And you might ask if these proteins are important, and I will remind you that when you're missing factor 8, F8 here, you have hemophilia. So indeed, these proteins are absolutely important. If you take Coumadin, you take warfarin, you have low levels of 4 of these proteins that require vitamin K. So blood coagulation is very important for generating fibrin. Now this is what Richard Furie saw 10 years ago. This is a system that we developed in our own laboratory to study blood coagulation in a living animal, in a mouse. And at this point, I probably have $2 million invested in this system, but it allows us to actually take a living mouse, put it under the microscope, and visualize clot formation as it's actually happening. And that's never been done before the way we've done it. Now, I have to tell you, this very much is a family affair. It's not just Richard. Richard is the one who got us into lupus research, but I've been working with my wife, Barbara, for over 40 years now, and we run our laboratory together. And one of the best parts of having children is to have a child who can help you with your work, ultimately. And we have a son who's a computer engineer in the film industry. And as I was trying to build the system, I was using him to help me do this because this is beyond my technical ability to go digital, to build a digital system for actually imaging clot formation. And my son kept arguing, you can do it, you can do it. He knows nothing about biology, though, but he knows a lot about how to store data, how to capture data, how to do image analysis, and so on. So this has been very much involved a number of us. And so I want to show you how this works. Here we're looking in real time at the formation of a blood clot in a mouse. we've made an injury on the vessel wall. This is an artery. And the colors that you see are coloring specific components. Tissue factor, remember the thing that turns on the blood coagulation, is green. Fibrin is blue. And platelets are red. And black and white gives us the image of the histology of the tissue around the blood clot. So we're actually watching the generation of a blood clot in real time. So this is the essence of the system, and this is what happens to all of us when we cut ourselves. It looks just like this. And just 2 weeks ago, we've upgraded our system so we even do better now. Look how much prettier these images are. And in this case, fibrin is green, platelets are red, and the two of them together can be seen here. We can now do this in 5 colors. We can choose 5 different things to color so we can watch all of these things happening at the same time. I won't tell you how many megabytes, gigabytes we need to collect this, but we just bought a 62 terabyte array. We're storing the data. A terabyte is 1,000 gigabytes. So you can imagine what the problem of storage of this kind of information. So let's come back to the antiphospholipid syndrome and give you a hint of what the problem is. One of the questions that we asked was whether the antibody to beta-2 glycoprotein 1 was actually a biomarker or was it actually pathologic? Did it cause problems? And here we're making a platelet thrombus in red, and we add 0, 0.12, and 0.4 micrograms of purified antibody, anti-beta-2 glycoprotein 1 antibody from one of Richard's patients. And you can see how much bigger the clot gets when you infuse this antibody. In fact, it gets over 100-fold greater. So this antibody isn't just a biomarker, it's causing some serious problems. And one of the goals of the project that we're working on is to understand what is this antibody aiming at, what is its target, and how can we block it? We can also look at enhanced platelet activation due to anti-beta-2 glycoprotein 1 antibody, and you can see that before the infusion of antibody, we have a small thrombus, and very few of the platelets are activated. Those are the ones that are yellow. But when we infuse the antibody, look how yellow and large this becomes. So this antibody is a real problem. And it's a common antibody in patients with lupus and in patients who have antiphospholipid syndrome. So what are the cell targets of the antibodies in antiphospholipid syndrome? How can we block these antibodies from doing harm? That's the fundamental question that we're asking. So you're beginning to get an idea of how we develop a piece of technology, we invest a lot of money in making it a state-of-the-art instrument that is unique, and then we identify problems that we can try to solve with that kind of instrumentation. Now, another serendipitous, accidental observation. Christian Amundsen was my postdoctoral mentor. He's the one I worked for a number of years ago, back in the Jurassic Age. And curious, he was at the NIH at the time, and he was studying a protein called the disulfide interchange protein, which was nicknamed in the lab as the reshufflase, because it reshuffled what are called disulfide bonds, pieces of proteins that hold things together and give proteins their structure. And he was a very famous protein chemist. In fact, while I was in the laboratory, he won the Nobel Prize. This is the week of Nobel Prizes, and I remember that that day when I came into the lab, and suddenly I was surrounded by 35 reporters trying, because they couldn't get near him. They had it set for me. And the protein that he discovered was protein disulfide isomerase. Every person who's ever studied biochemistry knows about protein disulfide isomerase. It's inside the cells, and inside the cells, it's responsible for making disulfide bonds, where it's part of making proteins. Little did I ever think I was ever going to be interested in protein disulfide isomerase, which I'm going to now call by its nickname PDI, protein disulfide isomerase. And what we now know is protein disulfide isomerase, which is up here on the top, not only has 4 separate domains, but it's part of a whole family of related proteins. We don't need to go into any detail other than to say that these enzymes are very important in making proteins inside cells. No one has ever suggested that this protein has anything to do with blood coagulation. No one. And we stumbled on that quite accidentally. We'll get it to move there. So the question is this class of proteins, the PDI antigens, are they expressed in thrombus formation after tissue injury? We had a reason to explore this, but we looked in the mouse. As we made a thrombus, we looked to see whether PDI was secreted, which is in green, or another part of the PDI family, ERP5, ERP57. And you can see it's getting squirted out as we look at this. No one ever anticipated this. Completely accidental observation. But you see PDI being squirted out, and I'll tell you now, it's coming from the endothelium, the cells that line the blood vessel, and it's coming from platelets, the small cells that circulate in our blood and become an intimate part of the thrombus. And I want to show you, I've shown you that PDI gets squirted out. I didn't tell you that it has any function. And the way you test that is, whoops, what's happening here? The way we test that is to look at thrombus formation in the absence of PDI and in the presence of PDI. And in the way we've done this right now is to look at platelet and fibrin generation in a wild-type mouse. Carla mentioned that word. In other words, a normal, everyday laboratory mouse. And when we add an antibody that inhibits PDI, we can see that no platelets and no fibrin are generated. This was really shocking. This is remarkable. We had no anticipation of this. So if this inhibited thrombus formation, could we actually develop a drug that would block PDI and therefore prevent thrombus formation? Wouldn't it be nice to get rid of warfarin? I'd love to get rid of dabigatran too, Pradaxa. That's the bane of my existence right now. And rivaroxaban and these other drugs that you see on television all the time. That's another story. So the way we did this is to take PDI and do a high throughput screen. That's a fancy way of saying we assayed thousands and thousands and thousands of compounds in automated systems to identify anything that would inhibit PDI. And indeed, we identified quercetin-3 rutinoside as a compound that inhibits PDI. And just to show you it inhibits PDI, here's our thrombus being made again. Yes, there we go. And in the presence of rutin, it's completely blocked. What's interesting about rutin is that it's in onions and apples and all kinds of vegetables, and you can buy it at your local CVS. Don't go out and buy it though, not yet. But you can buy it, it's an alternative medicine. But it's never been explored in this fashion. And of course, we have no idea previously that it had anything to do with blood coagulation. So, rutin is a widely consumed flavonol. The FDA has already designated it as safe, generally recognized as safe. It's safely used at high concentrations, well exceeding that used to inhibit PDI. And there's epidemiologic literature that shows that it has a cardioprotective effect. And when we published this last year, suddenly the lay press picked it up, and herbal supplements may prevent dangerous blood clots. Rutin, a chemical that can prevent blood clots. Prevent blood clotting by apples. Remember the apple a day? Rutin may prevent #1 killer of Americans, and rutin becomes of interest for its stroke prevention powers. Onions could save thousands of lives by preventing blood clots. So the question we have is, can this be used in lupus and antiphospholipid syndrome? And going back to our mouse, in which we have this mouse model in which we infuse the antibody anti-beta-2 glycoprotein 1, we can show that we get a very large clot, as I've shown you already, both a fibrin clot and a platelet clot. But notice that in the presence of rutin, it's completely blocked. And now we're in the process of doing clinical trials, first in mice. Mice are easier to do than humans. I leave the humans to my brother. But we're using isoquercetin, the first cousin of rutin, and we've shown that if we take a compound that induces clots in mice, that compound being thrombin, we can kill most of the mice in 5 minutes due to clotting. But if we give them increasing amounts of isoquercetin, this blocks this effect. So we're working on the details of this, and we are simultaneously beginning a clinical trial to explore whether we can prevent blood clotting in cancer patients. So the conclusions are, can we better understand the mechanism by which beta-2 glycoprotein 1 antibodies enhance thrombus formation? And secondly, can we use this information to develop a novel, safe, efficacious therapy to prevent thrombus formation in patients with lupus? So with that, I will stop, and thank you very much.